Hey folks, Todd Coburn here with your Aerospace Structures series. This lecture is on effective sheet widths and on inter-rivet buckling. These two topics do go together, and this is why they're included in the same video. So let's see how it works. So you may have noticed that in life, sometimes some folks don't act alone. For example, on the rugby field, these guys will typically not be found running by themselves. They will be running as a pack, bound together, and moving as a team toward their objective of scoring that goal. They tackle together. They run the ball together. They push together for the goal. The weakness of any one member is offset by the strengths of the others. And therefore, one of the players is not destroyed by themselves because they are bolstered and their performance is augmented by the team. Aerospace structures are people too, and they act in much the same way. If you look at an aerospace structure such as this one, you'll notice that the stringers don't act alone. If one stringer starts to give way or starts to yield or starts to cripple even, it will shed load and share load as its stiffness softens, and the other members, which are unsoftened, will pick up that load. This is true for the stringers and for the frames, for the floor beams, for the window belt, and for many other of the redundant structures that we find in aerospace and other structures. When we look at a typical piece of aircraft structure, we'll see a frame which is stiffening the ring and distributing floor loads to the skin. We'll have the stringers like these little Z stringers or J stringers that I have sketched in there that run longitudinally and carry most of the bending loads of the fuselage. We'll have shear ties which allow the frame to float above the stringers and that tie those frames to the skin so that the skin and frame act together as a single, more stiff and more efficient bending member. We'll have little stringer clips which tie the frame to the stringers so the stringers get supported at each frame out of plane and to tie the frame down even slightly more. And then we'll have little tear strips which are in there to help arrest cracks that may run longitudinally or in the circumferential direction on your fuselage structure. Because we have so many lightweight members interacting and working together, and we will keep our analysis simple by analyzing often one of these members for a single load at a time, like a stringer for just axial load, the shear ties, the shear clips as just carrying the shear, the frames is carrying axial load and bending with some shear, and the skin, which is assisting with the stringers in carrying that load. To ignore the skin is to ignore a lot of the structural strength that it adds to the frame and to the stringers. So we want to account for it. However, because the skin tends to be soft and buckle out of the way easily, what happens is we can't account for the full width without being unconservative for many of the loads that we're going to see. So what effective widths are going to allow us to do is to understand or predict a good approximation of how much of that skin, when we have thin members attached to little stiffer members, how much of that thin skin-like member will be acting with a frame or with a stringer or with other members. And that's what we're after today. So let's take a look at how it works. What happens is you have, so if we focus on the stringers, for example, and we have a thin skin with longitudinal stringers, the stringers have some stiffness, are primarily axial load-carrying members, which, because they're distributed at different positions, they carry the bending in the fuselage. And as we have low loads, we get increasing stresses on the skin and stringer that are distributed at the same stress value. But as our stress climbs, the skin begins to get softer as it approaches its buckling allowable. And so as the stress climbs, the skin between the bays or between the stringers will tend to pick up less and less of the increasing load, while the skin near the stringers will tend to continue to climb in increasing load, which means increasing stress. So we're going to see the stringer stress increasing further and further, and the skin in the vicinity of the stringer increasing further and further, but the skin between the stringers, where it's not supported by the stringers, not carrying the same proportion of increasing load. So we'll see a nonlinear distribution of stress develop in the skin as the skin near the stringer picks up load, but the skin between the stringers doesn't. In the end, we're going to end up with a rather complicated distribution of stress. And because of the challenges in calculating that accurately, what we will often do is just account for, okay, let's just assume that a certain amount of the skin acts with the stringer. And the skin and stringer, the skin in the vicinity of the stringer, or the effective width of skin, acts at the same stress level as the stringer, but the skin between the effective width of skin we will just ignore completely. What this allows us to do is focus on analyzing the stringers for the axial load, and the adjacent skin that is acting with it, we pretend that that carries the same stress level, but the skin away from that effective width, that's outside of that effective width, we will just ignore altogether. And that is our assumption that we will use. I'm going to use a graphic from Brune that I developed a few years ago. This is a sketch from E.F. Brune's analysis and design of flight vehicle structures. We can see three stringers here. I've modified the figure a little bit, and we see at low stresses, as we increase the loading on the compressive load on the skin and stringer combination, we see the stress level climb, gets larger and larger and larger, as long as the stresses are down in the elastic range. As the stresses climb up and the stress now passes the buckling allowable of the skin, we see that the skin between the stringers carries less and less of that load, and while the skin in the vicinity of the stringer continues to pick up additional load and therefore additional stress, getting a distribution of stress like this. In the extreme, we will pretend that instead of that nonlinear distribution of stress, we'll just pretend that the skin near the stringer in the effective width part, or the part of the skin that we're going to assume is working with the stringer, we're going to assume that that's at a constant stress level the same as the stringer. And the skin between the stringers will be at a zero stress level. We'll ignore it altogether. To look at this graphic again, we see that under low stresses, we have a distribution of stress like this. As the stress level increases, we see that parabolic distribution of stress developing, and yet we're going to ignore all that and just assume that an effective width of skin is working with the stringer and carrying that load. So that is how we're going to approximate the behavior of the skin stringer structure, and any structures like that where we have lump-like members carrying axial load or bending and some amount of thin skin that may buckle out at a low load. Okay, so let's derive this. If we focus on our stringers and the skin between them, we recognize that every 20 inches or so, we're going to have a frame, and that's going to support both the skin and the stringer to keep it from buckling. Therefore, if we focus on the buckling allowable of that skin between the stringers and between the frames, we can write our buckling equation from our flat panel buckling equation that we saw 2 lectures ago. And this is that equation. If we assume simply supported edges all the way around the panel, that means both at the ends and along those edges, we get a buckling coefficient of 4, and we can actually plug in our frame spacing and our stringer spacing and such, and rearrange, and we can write the equation like this. So we basically solve for leaving the buckling allowable in the equation and solve for the effective width the effective width that holds the same allowable as the stringer. So once again, if you look at this, we've got the critical buckling stress for that panel. And what we've chosen to do is now solve for that W, that width of the panel, that supports a certain stress level. So if we plug in the buckling allowable of the stringer in that FCR position, we will end up calculating the effective width of skin that will support the same allowable. Normally we use this equation. We plug in the width of the stringers and we get an allowable stress at which the skin will buckle at. And yet what we want to do is figure out how much of that skin or what width of skin actually will sustain the compressive allowable of the stringer. So we take that FCR and assume that that is the stringer buckling allowable, and now we solve for W, or the effective width of the skin that acts the same stress level. We end up with this relation, W effective equals 1.9 times T square root of the compressive modulus divided by whatever the allowable of that stringer is. We've still got it shown as F critical, okay? This allows us to know then how much effective width W of the skin acts with the stringer and supports the same buckling allowable. Now, of course, we saw before those panels were supported at the stringers and at the ends, and now what we're basically doing is focusing in right around the stringer and saying what effective width of skin is supporting it, as if it was supported simply on each edge of that panel. Okay, so that's a little bit of an assumption, but that's the way we do that. Okay, we can now insert FCY instead of FCR, or the crippling allowable instead of FCR, or whatever the stringer compressive allowable is instead of FCR, and get different ways of calculating the effective width. Okay, we're going to talk about this further, but this basically sets our minds on the derivation of where this comes from. Once again, we just calculated, we took that flat panel buckling, so the fuselage skin is not flat, but it's an approximation to assume that it's flat, that the curvature is large enough to approximate that behavior as a flat panel. And then we solved for what effective width will support the buckling allowable of the stringer, where we have that E, compressive E, is the compressive modulus of the skin that supports that F critical of the stringer itself. Okay? If you've kind of got your mind set on that, you're ready to move forward. If you don't quite have it, you almost have it, it's okay, because I'm going to give you some really clear equations that are simple to implement in a moment. Okay, so the design equations then that we have are like this. We have this assumption of how much effective width of skin is acting with the stringer. And if we actually had a skin that was 2024 sheet, then we're going to get a compressive modulus of about 10.7 million psi and a yield strength of about 40 ksi. If you plug these values into our little design equation, you find that our effective width is about 31.1 times whatever the skin thickness is. If instead we had 7075 T6 sheet, we'd get an E sub C of 10.5 million, yield strength of about 70 ksi, and we would have found that our effective width is about 23.3 times the skin thickness. What these design equations basically mean is if we have 2024 skin, without doing a whole lot of fancy calculation, we can assume about 31 T is the effective width of skin, the total effective width of skin per fastener tying the stringer to the skin. If we have 7075, we can assume it's about 23. Because of these equations, because a lot of the older skins were 2024 and the current skins actually, it's common to use a design equation of 30T. Basically a gross approximation, but it basically says, hey, if we don't really know what the effective width of skin is, we don't know a lot about the design, we can just pretend that about 30 times the thickness of the skin acts with the stringer as one. So if we have a stringer like the Z stringer, and if it's fastened, say, with a line of rivets, a single line of rivets, we could assume about 30 times the skin thickness is how much width we're going to get acting with the stringer as one, and that would support the design allowable or the buckling allowable of that stringer. This is how this equation comes into being. Got it? Okay. So if we look at that further, we see if 30 times the thickness is the width of skin acting with the stringer, then that means 15T on one side and 15T on the other side of that fastener. That can be a useful relation when we're accounting for multiple fasteners through the stringers. We'll talk about that again in a moment. All right. So one caveat before we move on. Now that was for stringers that are running through a continuous skin. If we actually have a stringer falling right at the edge of the skin, we can then go and look at our plate buckling equation when we had 3 simply supported sides and 1 free edge. Because if the skin is ending there, then that skin may be free. If that skin is free, we're going to have a different buckling coefficient for that panel. If we plug in the buckling coefficient for a 3 sides simply supported on that panel, 1 side free, our buckling coefficient is 0.43, and that gives us a reduced equation of an effective width of about 0.62T instead of 1.9T times that square root of E sub C over the stringer allowable. And I'm using the nomenclature FST as just an approximate number of whatever that stringer is good for, rather than the FCR, which had the idea of panel buckling. Okay? All right, so let's see how we can use this. Let's say we have a stringer, and let's say we have skin that's attached to it with a line of fasteners. Assuming that that line of fasteners gives sufficient support, we can calculate our effective width. And I'm going to give you basically a set of equations to choose from. Early in the design, it's common to use that effective width, that 30T, as an approximate value. So let's say you're designing an aircraft, you don't know anything about the aircraft, you know roughly how many stringers you want and roughly what your skin thicknesses are, and you haven't really selected materials. This would be a great time to assume that 30 times the thickness of skin is going to act with the stringer. So this 30T value can be used whenever we know nothing about the design except skin thickness and where the stringers are going to go. We can use this to say, okay, we can account for about 30 times the thickness acting with the stringer, okay? Now, as we move on in the design to a little more mature design, still an early design phase, we may have already chosen material for the skins. Once you have material for the skins, then there's no reason to be so approximate as 30T, because we've already seen that actually with 70-75, it's only 23T. So in that case, we should do a calculation and plug in the FCY of the material. So in that case, we will replace that F critical or FST with FCY. So basically, we can approximate now the effective width of skin by taking the compressive modulus of the skin, the yield strength of the stringer, because that's what we're approximating is the strength of the stringer. That's what we want to support with the skin, and the thickness of the skin to calculate what effective width is appropriate. So this is going to give us a slightly better approximation for how much effective width acts with the stringer. Okay? Now, as our design matures, we're going to eventually calculate, not only know what the skin thicknesses are, but the materials and the crippling allowables. We'll be calculating those. Once we know the crippling allowable, this is really the best number to stick in here. So you're going to have the compressive modulus of the skin divided by the crippling allowable of the stringer itself. Normally, you could actually include the skin with the stringer when calculating that crippling allowable, but you get in kind of a going around and around kind of analysis, chasing your tail. So Bruhn recommends, and I agree, that you will just calculate the crippling allowable of the stringer acting by itself. Plug that in here along with the E sub C of the skin, and that will give you a fairly good approximation of the effective width of skin for the remainder of the design period once your design is mature. Okay? If we end up finding ourselves on the edge of the panel, you can use this relation. So that's how that works. All right. Now that you understand how to calculate the effective width of skin, then I need to warn you about some tricks and traps. So we've been focused on a single stringer with one line of fasteners. However, if we have more than one line of fasteners, then we're going to have an effective width, because every single fastener that goes into the skin is going to invite additional skin to help us. So if we have 2 fasteners, we feasibly could have twice the effective width of skin. If we have 3 fasteners, we could feasibly have 3 times the effective width of skin. Okay? And so whenever we see multiple fasteners, we say, oh, great. That means not only do we have the stringer, but we also have 1 or 2 or 3 or maybe even more times the effective width of skin acting with it, because every fastener through the skin invites more skin to assist. Got it? Now, however, you've got to be a little careful, and here's why. Take a look at this guy. Here's a stringer, and it has 2 fasteners. So normally you think, okay, we can use effective width of skin for both. And if these fasteners are far enough apart, then that's true, because you can see if we have 2 fasteners that are spaced like this or like this or like this, we still have 2 times the effective width of skin. But let's say those 2 fasteners are really close together, like you see in this picture. Then these 2 effective widths overlap, and if we use twice the effective width of skin, we're going to actually be double counting for this part of the skin between the fasteners. And so that's not acceptable. So what we need to do is adjust our number to check how close are these fasteners, and can we account for all of the effective width, both fasteners inviting both full effective widths or something less. Here's how it works. So this little design equation will get you around that. If you have multiple fasteners, you can use W effective over 2. That's the part of the skin on the left side of the leftmost fastener, and W effective over 2, which is the stuff to the right of the rightmost fastener. And between them, you can check the minimum of the spacing between the fasteners and the W effective. Whichever is smaller will govern. If these are too close together, then it will be the spacing that governs that middle piece, because we can't have more effective width than what skin actually occurs there. If we have our spacing is large enough, if it's larger than the effective width of skin, then we don't want to use more than is effective, and therefore use effective the W effective. So W effective over 2 plus W effective over 2 plus the minimum of either the spacing or W effective between those. Now, if any of these occurs on the edge of the panel, you can just adjust it by using that half equation of our edge equation we saw before. Got it? So how does this actually work? Well, let's say we have a stringer like the Z stringer with some skin applied, and we want to know what benefit does it have. Let's say that we account for how much. We've got 3 different ways, right? We can assume 30T, or we can calculate the W effective based on FCY if we know a little more about the design. If we know everything about the design, we'll take the crippling allowable of the stringer and use that in our W effective equation to calculate how much of the skin acts with the stringer. Okay? But once we have that value, how do we do that? Well, let's just say that we've already figured out what our stringer properties are. We've got an area and a Y bar and an I, and we calculated what our effective width of skin is, and for some reason, we're using the 30T approximation. Great. Now what we want to do is calculate what are the buckling allowables of the stringer when you account for both the stringer itself and the skin that acts with it. And in that case, you'll set up a little table to calculate the new properties. What's going to happen is that effective width of skin will add to the area and to the moment of inertia, and it will change your Y bar a little bit. So you can construct a little table. We can put the stringer in one line and the skin in another line. And we already have the properties of the stringer. That's given. So you've got the A, the Y bar, and the I of the stringer, as you see in the first row. In the second row, we have the skin. So we calculate what that effective width is and what the thickness is. We calculate the area of that and its Y bar relative to our starting point. In this particular case, you'll notice that I'm using the Y bar of the stringer from the bottom of the stringer, and I'm using the skin as down below my reference axis. Therefore, the skin Y bar is at half the thickness below my my origin of the y-axis. And then I calculate the 112 BH cubed or BT cubed stiffness of the skin, and I can calculate my new properties, my new area, my new y-bar, my new I of the combined section. Then we can use those values in the Euler buckling allowable, going back to what we saw about columns. And that we'll find that actually that gives us a higher allowable buckling load than we would have had if we hadn't accounted for that skin stiffness. Why? Because the skin added area and it added moment of inertia and increased the moment of inertia of that combined section. Okay, so that's how we're going to use it. In this particular case, we end up the effective width of skin increased the moment of inertia by 2 times. That's a big help for a lightweight structure. This really allows us to have more efficient design when we account for these kinds of things. Okay, so that's how it works. Now, before we get too excited, we need to watch out because it's possible that we can't develop the entire effective width of skin that our earlier approach assumes. And the reason for that is what we call inter-rivet buckling. So all of these little fasteners that are attaching our stringers to the skin, we can say that they're rivets. They may be rivets. They may be hylocks or something else. We call it inter-rivet buckling, but really it's inter-fastener buckling. Okay? We're basically assuming that that skin acts monolithically with the stringer. Monolithically means like a rock, as one, which means the skin and the stringer are acting together. That's the piece of skin that we're calling that effective width of skin. So what happens is that assumes that the skin doesn't budge. However, if you take a look at the skin right there between the rivets, so we see here we've got a single row of fasteners, but that means we have a rivet here, and back in the page we have another one, back in the page we have another one. So actually all of these little effective widths of skin are being compressed longitudinally, as you see in the second picture. That's looking at the side of the stringer, and we can see if these fasteners are spaced too widely, what happens is, and if that skin is really thin, it will buckle between the stringers, or excuse me, between the fasteners as we see in this picture. That would mean that it's not developing the full compressive allowable of the stringer. So we need to keep it from buckling. If it buckles, that means that effective width of skin is incorrect. And so what we're going to do is we're going to come up with a simple way to adjust our effective width to make sure that we don't inter-rivet buckle under load. And here's how that works. Okay, so we take a look at a little rectangular section of skin with simple supported edges. Once again, as we did before, we can actually calculate the buckling allowable from the Euler buckling allowable like this. This is the form of the equation where we have a coefficient. We have that E, which actually is shown ET because this is the tangent modulus, but really that's the compressive modulus of the material, right, of the skin. The compressive modulus of the skin. I'm showing ET here to remind us that it's a tangent modulus would be the most correct, but generally we'll just plug in E sub C here, okay? We get the L prime over rho, or rho is the radius of gyration of the skin, the square root of I over A, okay? So that is our Euler buckling equation for that thin plate of skin, treating it like a column, okay? If we say that the column length is the rivet spacing S, we plug in the moment of inertia per inch, that's 112 BH cubed, or 112 BT cubed. Without the width dimension, we'll make it a per inch basis. And the area is just B times T, but if we just say T, it's just a per width basis. Therefore, our radius of gyration is actually the square root of I over A, which is 0.29 T, and we can write this equation like this. And you've noticed I've switched the E, the modulus, to E sub C, that compressive modulus of the skin. So this is developed for a flat panel, but we're focused between the rivets, treating the skin between the rivets as a little column and of unit width, and therefore the inter-rivet buckling allowable of that little column of skin is given by this equation. This equation can be used for any end fixity of those rivets. But there's been some work done that comes up with some effective width of some coefficients. Basically, if we have flat head rivets, protruding head rivets, we could assume that our coefficient is 4, like a pin support, and therefore we would have our inter-rivet buckling allowable would be pi squared E sub c over the spacing times, which is over 0.58 t, all that quantity squared. So this equation, if we have other end fixities or other head types on our rivets, we could assume that our C is 3.5 or 3.0 or 1.0, depending, as we see here. We just plug in that other C value and use this equation, the more general equation, to estimate our inter-rivet buckling allowable. Okay, so that's how we do it. So you've seen how to calculate effective width of skin, and we've seen how to calculate the inter-rivet buckling allowable. We haven't yet seen how to put these two pieces of information together. That's what we're going to do next, so stay tuned. All right, so here's how we use inter-rivet buckling. What we're going to do, so it's important that we don't buckle between the rivets when we're under compression, and we chose our effective width of skin as the value that should be able to support the full crippling allowable or compressive allowable of the stringer. So if our skin buckles between the rivets, and that means we failed in our goal of coming up with how much effective width of skin acts with the stringer without having a problem. So what we're going to do, because once the stringer buckles, the skin is not going to help. So what we'll just do is we'll check the inter-rivet buckling against the crippling allowable. If our inter-rivet buckling allowable of the skin between the fasteners is greater than or equal to our crippling allowable of the stringer, then that means that effective width of skin that we calculated is correct, and it will support the full crippling allowable of the stringer when we assume that width. Okay? If our inter-rivet buckling allowable is less of the skin is less than the crippling allowable of the stringer, then that means that that skin will buckle between the rivets before you get to the crippling allowable of the stringer. That means that the effective width of skin will not make it to the full crippling allowable before buckling. For this reason, we will use a modified value. Here I'm calling it W effective corrected. We're going to take the W effective that we calculated. We're going to multiply it by the ratio of the inter-rivet buckling allowable divided by the crippling allowable of the stringer. And that will give us a corrected. That will have the effect of reducing our effective width to the value that will sustain all the way up to the crippling allowable of the stringer. Okay? Another way to describe this is to say, if we call all of our earlier calculations for effective width as W effective prime, and then once you check and correct that value, that becomes the W effective value. Or you can call it the corrected value, as I say here and as I show in the handbook, okay? Now, one word of warning. We're not going to use the inter-rivet buckling allowable to increase the effective width of the skin. The effective width of the skin was chosen to make sure that the skin buckling will support that stringer crippling. The effective width, the crippling adjustment, the inter-rivet buckling adjustment is to make sure that that little column of skin doesn't buckle between the rivets before it supports that other number. So we're going to first calculate the effective width of skin, the pristine value, W effective prime. Then we're going to calculate our inter-rivet buckling allowable, take the ratio. If our inter-rivet buckling allowable is less than our crippling allowable of the stringer, we will adjust our effective width using this equation. If our inter-rivet buckling allowable is the same as or greater than our crippling allowable of the stringer, then no adjustment to the effective width is needed. We will not use this equation to increase the effective width of skin. That would be wrong, unconservative, and can result in catastrophic results. Okay? So that's how we do it. Then we would continue on. That example we saw on the last page would be the same, or two slides ago, will be the same as before, only now after we've evaluated what the effective width of skin is, we would then check to make sure it's not inter-rivet buckling and adjust if it is. Okay, so you now are armed and dangerous. You know how to calculate the effective width of skin using three methods, one for preliminary design, one for early design, and one for mature design. You know how to calculate the inter-rivet buckling allowable, and you know how to adjust the effective width of skin if the inter-rivet buckling allowable is less than your crippling allowable of the stringer. You can use these techniques in everyday design and analysis to evaluate the effect that thin skins have on members that they're attached to, the bolstering method, without over accounting for their buckling strength. Hope you found this useful. If you did enjoy this video, this free video, I'm going to encourage you to hit the like button. Make sure you subscribe. This will keep you connected with the data and my updates. And it will also help me to know that you're interested, and it will also make it easier for others to find this video that may also need to benefit from these kind of ideas. Okay? Go out there and be great. Thanks for tuning in. Enjoy.